There are a myriad of different fire ground factors. It's impossible for the IC to consider every single factor prior to taking action. The time temperature curve of real-world fire operations allows the IC a very short time to evaluate a handful of fire ground factors when conducting a size-up, formulating an incident action plan, and taking effective action. The factors that directly impact the IC's ability to complete the tactical priorities and provide for firefighter safety can be best defined as the critical factors. A critical factor present at every structure fire we respond to is how well that particular type of building construction holds up under fire conditions. The performance of the various construction types is most often studied and observed under live fire conditions, while we're trying to save the building's occupants and extinguish the fire. Little has been done to look at the new construction types and how they perform under fire conditions before an actual event. Residential fires are one of the most common fires the fire service responds to on a day-to-day basis. It is vital that firefighters, company, and command officers know how these structures are put together and how the different construction types affect both fire behavior and the safety of firefighters. There are more old homes than new homes, but the new home construction methods present the fire service with a much more difficult set of critical factors to consider on these types of dwellings. In order to properly size up and implement an intelligent fire attack, we need to take a look at how both the old and the new homes are constructed. Prior to the late 60s, residential roof construction was of the so-called conventional type framing. This type of roof structure was characterized by a large continuous ridge beam and rafters made of 2x4s or 2x6s that were angle cut at the top and then nailed into the ridge beam. These rafters, beams, and purlins were continuous, uninterrupted wood members. Each of the rafters were nailed into place using several large nails which penetrated the entire rafter and almost all of the ridge beam. In order for a conventionally framed roof to fail, the rafters, ridge beams, or purlins must either break or burn through completely, and any failure of one of these members would not typically cause a catastrophic failure of the entire truss or the additional failure of adjacent trusses. Conventionally framed roof systems were usually sheeted with 1/2 inch or thicker plywood or with 1x6 inch skip sheeting. These materials were used to form a solid roofing deck. The deck was then covered with asphalt shingles, tile, or other roofing material. Conventionally framed roof systems were phased out in the late 60s and early 70s in favor of a prefabricated lightweight wood truss roof system. With the housing boom during this period, the new roof system proved to be more economical, more consistent, and quicker to erect for contractors. These trusses are more engineered than the old roof system and are able to carry greater loads than conventional framing. Oftentimes, the trusses don't require bearing interior walls to span large areas. However, this new roof system construction has been shown to have a more rapid collapse time once fire penetrates or involves the truss space as opposed to conventional framing. The lightweight truss system consists of non-continuous members that are butted together and then held in place by non-continuous nailing plates known as gusset plates. Gusset plates have multiple teeth that are pressed into the wood members during the prefabbed assembly process. The depth of penetration of the gusset plate teeth is typically 3/8 to 1/2 inch. These gusset plates are the weak link in the truss system when they're exposed to fire. These plates absorb heat very rapidly. This heat is transferred to the teeth of the plate, and that causes the wood to char around the teeth. That, in turn, weakens the hold of the gusset plate on the truss's members. As the fire progresses, the gusset plate will literally fall out of the truss. When this happens, any additional weight, stress, or vibration on the truss will cause it to fail and collapse. These gusset plates hold all of the truss joints together, and as a result, when the first truss connection fails, the entire truss can collapse, often causing adjacent trusses to collapse as well. Another new product that has entered the construction scene around the country over the past 20 years is oriented strand board, or OSB. OSB is made of scraps of wood that are glued and pressed together and are typically formed into 4x8-foot sheets, similar to plywood. OSB is less expensive and more readily available in large quantities than plywood and is rapidly replacing plywood as the building material of choice. OSB is typically used for siding and roofing decks and is used in conjunction with the new lightweight truss system. The typical OSB thickness used for roof decks is 3/8 of an inch. It's always been suspected that OSB would have faster failure rates than plywood, since plywood is made of solid sheets of layered wood glued and then pressed together. Tile is also rapidly replacing asphalt roofing in most areas of the country. Tile roofs are more aesthetically pleasing to homeowners than asphalt roofs and will also last the entire life of the home. Tile presents many difficulties during rooftop operations, such as the uneven surface of most of the tile today makes maneuvering on the roof more difficult. Removing the tile prior to cutting a ventilation hole takes precious time away from ventilation operations, as opposed to the quicker cut times made on asphalt roofs. One of the biggest disadvantages of tile roofing is the sheer weight of a tile roof. Each 10 by 10 foot square of tile weighs about 1,000 pounds. This additional weight on the OSB roof deck and lightweight trusses will only increase the failure times of these structures when exposed to fire. This was the construction method used on the incident of July 1st, 1989, when Ladder 27 of the Phoenix Fire Department responded to a house fire in North Phoenix. The house was built in the mid-'80s, used lightweight wood trusses, the roof deck was sheeted with OSB, and then covered with tile shingles. Ladder 27 arrived on scene about 10 minutes after dispatch and were ordered to the roof to ventilate a working attic fire. After about 7 minutes on scene, the 4-person crew had successfully ventilated the roof, and then the roof started to collapse around them. 3 members fell partially into the attic space, and 1 member fell completely into the attic space. All firefighters successfully extricated themselves from the attic space and made their way safely off the roof. All members had on full protective clothing, which include bunker pants and hoods, and all were wearing SCBAs with their face pieces in place and breathing air. Only the member who fell completely into the attic suffered any injuries, and those were minor burns to the hands and the thigh. While this incident is a testimonial to wearing full protective clothing at all times while working on the fire scene, it also showed us the inherent risk of operating on and around this type of construction. After the fire, the trusses were inspected. They showed that only 20 to 30% of the wood was consumed in the fire, but most of the trusses exposed to the fire were missing several gusset plates. This prompted an operational change in the Phoenix Fire Department.
The event that you just looked at in this video is obviously pretty exciting. In fact, it ought to be in the Close Call Hall of Fame. And it was a notable experience for our department and a very educational one. And we're obviously we were very, very thankful for the way it turned out. One of the things that we changed in our operations just based on that one experience and a lot of other close calls that we had was that we stopped conducting roof operations in lightweight constructed buildings where we knew or suspected that there was a fire in that truss loft, in those situations where those roofs were covered with tile, and we've been doing that ever since. We've had a chance here recently, and you're going to see in these 3 videos in this series, a relationship that we have developed with the National Institute of Standards and Technology, which is NIST, as they call themselves, to do a bit of a more scientific approach to looking at how these buildings that are lightweight constructed in the first video, how they behave under fire conditions, and the time frames and just what are the dynamics of how those buildings are going to react when they're burning down. It was a unique experience for us to get to stand back from what we normally are very actively and intensely involved in and be able to see how that fire progresses starting from ignition going through the standard fire stages. That has been a very, very educational experience for us, and I think you're going to see it in these videos. And that a lot of the assumptions that we had about particularly time frames on the fire ground have been shortened based on what we got out of these videos. And many of us were raised with the old 20-minute rule that has served us pretty well. But I think you're going to see in all of the test burns that we did, none of those roofs held up 20 minutes. What our objective is in this series is to provide better information to fire officers simply to make more effective and safer decisions on the fire ground.
The Phoenix Fire Department and the National Institute of Standards and Technology, or NIST, recently conducted live fire testing of 4 different residential roof systems in an effort to establish safety limits for safe firefighting operations. 4 separate structures were built and set on fire. Each structure was identical in the following ways. They were all 400 square feet and had the same layout. Each one had a kitchen, bedroom, and a living room. It's important to note that all 4 buildings used wood trusses as the roof structure. They were made of frame construction and covered with exterior siding. All the attics were insulated with rolled fiberglass insulation. The interior was finished with both plywood siding and drywall. They were furnished with the same furniture, and the floors were carpeted. The test measured the collapse time of 4 different roof types. The different combinations of roof decks and coverings were plywood covered with asphalt shingles, OSB covered with asphalt shingles, plywood covered with roof tile, and OSB covered with roof tile. Each roof carried a dead load that was made up of an AC unit that weighed 500 pounds and 2 dummies that weighed a total of 500 pounds, used to simulate a ventilation crew. Detection equipment was used to measure temperature and various fire gas levels. Special water-cooled cameras were used to record the interior fires. The fires were started with an electronically detonated book of matches that had been placed in the sofa and covered with a newspaper. The interior fires extended into the attic through a ceiling-mounted ventilation grate. All recorded times began when the book of matches was ignited and ended when the roof dummies fell into the attic. The first structure to be tested was the plywood covered with asphalt shingles. This roof failed 17 minutes and 31 seconds after the matches were ignited. The second structure to be tested was the OSB covered with asphalt shingles. This roof failed 16 minutes and 47 seconds after the matches were ignited. The third structure to be tested was the plywood covered with tile shingles. This roof failed 16 minutes and 4 seconds after the matches were first ignited. And the fourth structure to be tested was the OSB covered with tile shingles. This roof failed 16 minutes and 47 seconds after the matches were ignited. Let's take a look at a condensed time burn of the plywood roof deck using asphalt shingles.
5, 4, 3, 2, 1. Safety to command, be advised, we're trying to get some smoke out of that peak, right, in front of that standing firefighter. Out of 24 towards 24. Or 24. Firefighter first go in. Lead standing firefighter going in. Click crane 8. Man to crane 8. Pull out.
2 minutes after ignition, the burn area where the fire was started was well involved. 4 to 5 minutes after ignition, there were near blackout conditions throughout the entire structure. At the 6-minute mark, carbon monoxide levels and interior temperatures would be fatal to any unprotected occupants. The maximum temperatures in the living and bedroom areas reached temperatures between 1,000 and 1,500 degrees Fahrenheit. Flashover occurred in the living room and bedroom spaces between 3 to 4 minutes after ignition. The fires broke through into the attic spaces between 6 to 8 minutes after ignition. Flashover in the attic spaces occurred approximately 5.5 minutes after the fire penetrated the ceiling. On average, the fire flashed over in the attic 12 minutes after ignition. Prior to collapse, peak temperatures in the attic spaces reached 930 degrees. As the attic space approached flashover, the temperature on top of the roof quickly went from 100 degrees to 1,000 degrees Fahrenheit. Newer construction material and their newer contents burn very hot and very fast. None of the roof systems performed well. In fact, they all sustained structural damage after a very short exposure to the fire. The longest it took for roof failure to occur once the fire initially got into the attic was 9 minutes. The roofs sheeted with plywood and covered with asphalt shingles held together about a minute longer than the OSB and tile-covered roofs. The OSB sheeted roof with tile shingles had what would be considered a catastrophic collapse. This was due to the overall weight of the roofing material, causing the majority of the trusses to fail simultaneously. It's important to note that the dummies were a static dead load on the roof. They didn't move around, and they weren't using saws or axes to cut and beat holes into its structure that was being weakened by fire. A real live ladder crew would have probably caused the roof to collapse sooner and would have fallen into the attic quicker than the test dummies. Whether or not the attic space, especially the attic of trussed roofs, has any fire involvement will always be a critical fire ground factor. We have a very short window of opportunity to conduct safe and effective roof operations. After the attic spaces of the 4 test structures flashed over, the roof was no longer safe to operate on top of. Due to the hazards associated with lightweight construction and the increased difficulty of conducting ventilation operations on tile roofs, if there is a significant attic involvement, stay off the roof.